record and let me share. So in quiz 7, before you open it, there's no time limit on quiz 7. But what I'm going to do is I'm going to go through it with you. What I want you to do is open up quiz 7. If you can't open it right now, at least grab a piece of paper or make sure you go back through this video tonight. Quiz 7, as I said, is a worksheet. I'm going to go through it right now with you and answer these questions. And it's worth 5 points. Get it in, print it out, draw the free body diagrams, write the equations, and get it back to me. But as I said, I'm going to go through it right now. So I'll give you guys a second while I'm opening it to grab some paper, and we'll talk about these things. And if you've already done your homework, or if you have free body diagrams down, this might seem super simple. Some of you, though, I know are probably a little confused on free body diagrams. And so what I did was I created this problem that has 3 different masses attached by ropes. And we're going to do a free body diagram for each one, write the equations for each one, and then solve them. So essentially, it's like doing a whole problem together. Yeah, it doesn't have a time limit. You can open it right now and pull the PDF is in the description, so you should just be able to click on it and open it. But this problem is 3 masses. One's on an inclined plane, one's hanging, one's on a flat surface. All good, right? We're going to assume that this whole system is going to move in the direction from 1 to 3 down to 2. And so the point here is, on your exams, you're going to need to write free body diagrams for me. So we're going to write free body diagrams for these. Now, I'm not sure if I can draw on this, so I'm going to do something a little bit different here. I'm going to share my whole desktop. I'm going to create this, and I'm going to make a blank. All right, so back to this. So question 1 on the quiz is, I want you to draw the free body diagram for mass 1. So just for this mass. Remember that when we draw a free body diagram, what we do is we, and I don't know why I can't draw straight, I'm sorry, you guys. So it's attached by this rope. We just go down the checklist of forces. Everything that's on a surface has a normal, has a weight, it might have a tension, and it might have some random force. So here, just looking at this, we have to assume it has a normal force because it's on a surface. And we assume it has a weight because this is flat, this is M1G, and there's a rope, so we're going to assume there's a tension. And you just draw it straight up like that. Call it M1 though. Either call this weight 1 or M1G, and call this tension 1, because this is all mass 1. Now there's one more really super important thing that you always have to decide. Well, technically there's 2, but we usually assume that they're the same. You need to decide which way is positive in the X and Y directions. The weight is always in the negative X, or negative Y. But I'm going to assume my X is going to the right because this whole thing is moving to the right, right? I'm going to assume my acceleration is therefore going to be positive in that direction. Sorry if it's kind of dark.
Professor?
Yes.
Quick question about that.
Mm-hmm.
So when I think I texted you about this, but like, do you mind like elaborating on that? Because I remember for one of the homework problems, I made up the incline. For acceleration, I made up positive. I like somehow got a negative number.
Right.
Like I had to plug in negative acceleration for something.
So sometimes, and I know it's confusing, sometimes you're going to have like, I think the problem you're talking about specifically, we had a block that was being moved up the incline. When we turn this thing on its side and we get the forces, we obviously have a normal, and we'll come back to this soon, but, and we have a weight down the incline,
Mhm.
right? And so since it's initially going up, you might want to say that X and Y are positive in that direction, and it's moving with V. And so let's call A up. And what happens when you do that is you write MA in just the X, MA MG with a negative MG sine theta. And that's because the only thing in the X is MG sine theta,
Yeah.
and your A, you're assuming is to the right, MG sine theta is to the left, so it's negative. But,
Okay, that makes sense.
but
That makes sense. Okay.
we didn't need to necessarily. We could have done something a little different. We could have said that A was going to be positive down. And if it's positive down, then on our free body diagram for in the X direction, this is our equation. But if you do that, you better realize that B is originally negative. So it's
Okay.
weird.
Yeah.
The point of these is that we want to get some equation for X and then put it in the constant acceleration equations like this one. So what we're trying to do is solve A to put in here. And when you do this, if it had some initial velocity, if you went that way, then the initial velocity would have to be negative.
Yeah.
We'll get to that. It's a little confusing. The reason why I want you guys to draw an A is, what is a free body diagram for? It's not just an exercise in futility. It's not a way for me to just grade you on something random. The reason why we draw a free body diagram is it's a visual representation of our equations. That's why we break it into Y and X, so that we can write Newton's equation, which says MA is the sum of the forces. So here, I want you to write MAX and MAY. Looking at your free body diagram, assuming A goes that way, we know that the only force is T1. And I better write a 1 here. Whenever anything leaves the surface or cannot leave a surface, if it's on a surface and can't leave, there's no acceleration in that direction. I hope that makes sense to you guys. So N1 minus M1G. That's N1 because Y is up, minus M1G because the weight is down, because we chose this to be true. M1AX is positive because we chose that to be true. Does that make sense?
Yeah.
Okay.
Yes.
So this is all I want on this first part. I want you to draw this free body diagram right here. And I want you to list these two equations that you get from the free body diagram. I hope
So I
that.
have a quick question.
Uh-huh.
For the MAX, on one of the example problems we did last time in class was like the MAX was equal to MG sine of theta. Like, when do we know it's just going to be T of 1, or when do we know it's going to be MG sine of theta? Because I still have trouble determining
So
that.
we're on a flat surface. When you're on a flat surface, you go down these 4. The weight always points straight down. In fact, when we did the inclined plane, the weight went straight down.
Right.
But we broke it up into a weight down the incline and a weight perpendicular to the incline. We'll get to that when we do that. So here, you can just go down these. It only has a normal force if it's on a surface. It has a weight. And then looking at the problem, when I look at the picture of the problem, I see it's got a rope attached to it. And if it's got a rope, it's got to have a tension from that rope.
Right.
So that's all. That is all you have to do. And there's only those 4 forces. This F is because sometimes you're told like, oh, it's pushed with a force of blah. So you might have some random force vector to throw in there, but really this is all I want with A and Y of X, Y and X shown. So if I grade this out of 10 points, if you're missing the normal or the weight or the tension or A or this, pretty much you're going to lose 2 points for everything you're missing. There's a little wiggle room in there, but that's what I want. And the reason why I want those things is they enable you to go from this to Newton's equations visually. So on your sheet, just draw the free body diagram, write M1AX is equal to T1, M1AY is 0 is equal to N1 minus weight 1 or minus M1. Let's look at 2. And maybe this will help you a little bit. Normal, weight, force, and tension. So 2 looks like this. It's hanging by a rope. If we draw a free body diagram, is there a normal force? No. There's no normal force on something that's hanging because it's not on a surface. Okay. I'm going to assume that y is up positive, by the way, and x is right or left, but it doesn't matter. There aren't going to be any x forces. Does it have a weight? Everything has a weight. Weight 2 is equal to m2g. You can write it as either one. I don't care which one you write it as. Just know that that is the weight. Is there a force? No, there's no random forces. There is a tension because there's a rope, and I'm going to call this T2. Okay. And so from this, the acceleration is down. The acceleration is in the direction of the rope. So 1 is going to go to the right, 3 is going to go up, 2 is going to go down. They have to be consistent. You have to, when you do the one-on-one, A, 3A, and 2A. The A's all have to be consistent, and that has to be your direction of motion. All right, so what do we write? We write M2AX, M2AY. There are no forces in the X. In the Y, we said down was positive A, M2G minus T2. So that's all I want. I want this, and I want this. Does that make sense to everybody? Doing a hanging mass and then using that free body diagram to get your equations, okay? So you can put that here. 3 is going to be a little bit harder. We note that 3 is on an incline at some angle, and it's attached by 2 ropes. And we're assuming A is going to go up the incline. So first things first, if you remember from last time, we turned it on its side. And when we did, the weight still has to go straight down. In this, X would be like that and Y would be like that, and the weight goes straight down. Here, X is now along the incline. So we have this weight. This angle is actually the same as theta. To convince yourself of that, this is 90 degrees, so this is phi. This is 90 degrees, so this is phi, and this is theta. Therefore, this is the weight in the y hat, which is weight times cosine of theta because it's along this part right here. And then there's also a weight in the x, which is weight sine, because it's this same vector that would point like this, right? So what we have is we have a normal force straight off the surface. We have a weight in the x, which is M3G sine theta. We have a weight in the y, M3G cos theta. And then we have 2 ropes. Now, looking back at our picture, the rope attached to 1 is on the left side of 3. The rope attached to 2 is on the right side of 2. These have to be the same tensions. So T1 here has to be the same as, if I draw it like this, sorry. I draw it like this, and I draw it like this. The tension here and the tension here have to be a third law pair. because they're connected by the same rope. Same with the tension here and the tension here have to be a third law pair because they're connected by the same rope. If you look at this, tension 1 here, tension 1 here, tension 2 here, tension 2 here. So back to this, I need to make sure and draw tension 1 and tension 2 on mass 3. I already decided that this would be my X and this would be my Y, and I decided that A would be that way. It has to be consistent. So,
Professor,
yes.
why do we have to put the weight in the X direction if it's being pulled up? Like there's
It has, if you left it on a curve or on a if you left it like this, it has a weight, it has a normal, it has a tension 2, and it has a tension 1.
yeah.
The only one, if this is X and Y, the only one of these that you wouldn't have to break up would be the weight.
Okay.
But what we're doing is we're turning it on its side so that we don't have to break the normal into components. We don't have to break tension 1 and tension 2 into components. The
Okay.
only one we have left to break into components is this some weight in the Y, we're calling it, and some weight in the X. And that just saves us a lot of work when there's a lot of forces. I think your other question really was, why would it have a weight? It always has a weight. Everything on Earth has a weight attached to it. And you have to make sure that if you're breaking it, if you're turning it, you have to make sure you break it into the right components. So it has to have a weight in the Y and a weight in the X. So after all that, we got for 1, we got M1A X was T1, and we got M1A Y was 0, was N1 minus weight. And then for 2, we got M2AY, and I'll call that 2, let's put a little ones here, was M2G minus T2. Did I do that? Yeah, do that. Okay. And then finally for 3, if my stupid pen will work, I have M3AX3, M3AY3. This was N3 minus M3G copes. And this was T2 minus T1 minus M3G sine theta. Okay, so that's what these all, I guess I didn't write these, sorry. So in the Y direction, A3Y, it can't leave this surface. It can't go up and down off this surface. But you get N3 minus M3G cos. And that'll be useful when we do friction a little bit. But right now, you can kind of just throw away that equation. A3X is, since A was chosen to the right to be positive, T2 minus T1 minus M3G sine theta. So I want these free body
Professor,
diagrams. Yes.
could you go back really quickly to that slide? I was wondering for the bottom equation, T2 minus T1, since the tensions you're saying like in theory are equal, wouldn't they equal 0?
No, those tensions are not equal. The tensions between 1 and 3 are equal, and the tensions between 2 and 3 are equal. But there's no reason to believe that the tension here and the tension here are equal.
Okay, got it.
They're different third law pairs. Okay. And in fact, you can see what we're actually going to do is, since we're throwing away this equation, we have M3. Well, hang on, let me get to it. You'll see what I'm doing in a minute. So question 4, assuming you were able to do a free body diagram and your equations, which of the accelerations are the same? So let's go back and look at this. We have AY3, AX3, AX1, AY1, AY2. Now we know they can't leave the surface, so these ones I don't care about. But which of the accelerations have to be the same? Well, AX1 has to equal AX2, and it has to equal AX3. What that's saying in the picture is that the force along here and the force along here and the force along here for the system have to be the same. So why would the acceleration of 1, the acceleration of 3, and the acceleration of 2 along the direction of the rope be the same? Because we're assuming that the ropes are stretchless. If the ropes can't stretch, we're also assuming they're massless. But if they can't stretch, then if 3 moves up an inch, 1 moves to the right an inch, and 2 falls an inch, right? If 2 falls a mile, 3 moves up the incline a mile, 1 moves to the right a mile. So their displacement, velocity, and accelerations all have to be the same. Which ones are 0? The normal force and the weight along the perpendicular to the incline. There cannot be any movement off that incline. So we know that that's 0. And there's no x component to the acceleration of 2, so that's 0. And there's no y acceleration because 1 can't leave the surface. So essentially, m2ax2, these are all 0 because they can't leave the surface or there's just no force. So which of the accelerations are the same? A1x, A3x, and A2y are all the same. Why? Because they're massless, stretchless, frictionless ropes. If you read the practice exams, you'll see that's true. Which of the accelerations are 0? The ones that are perpendicular to the surfaces because they cannot leave the surfaces. Now, if the system moved with constant velocity, which accelerations would be 0? All of them. Constant velocity means 0 acceleration. You should know that from your homework, though. Okay.
Professor?
Yes, ma'am.
And like you said, once this is done recording, you'll post this on Canvas so we can go back and understand this too.
Yes.
Okay.
Yeah, if you have any questions, though, feel free to ask if I'm not being totally clear. And then finally, we're going to do something with our equations. So if we assume all the masses are 4 kilograms, and we assume the angle for mass 3 is 20 degrees.
Excuse me.
Yep.
For the previous question, I have questions for number which acceleration are 0. Can we say A1y and A2y and A3x is 0?
No, it's actually, so for A2, where was it? A2, we're assuming that AY is down. So A of x of 2, A2x is 0. But the more important thing is that there's no acceleration up or down for 1 because it can't leave the surface. And there's no acceleration up or down from the incline, perpendicular to the incline, for 3. And we labeled those, or I labeled those A1y and A3y, or AY3, AY1. Does that make sense for us?
No, not clearly.
Okay, so okay. Here's the thing. I'll try and do this as clear as possible. So for number 1, it's going to have an acceleration in the y, and it's going to have an acceleration in the x. For 3, once we put it on its incline, it's going to have an acceleration in the y and an acceleration in the x. And then for 2, it's going to have an acceleration in the y and, let's say, an acceleration in the x. And so what I'm asking you is which of these are 0 and why? A1, y, does that make sense for us?
Yes.
Okay, so A1y is going to be 0 because it can't leave the surface. Same for A3y. It can't leave the incline, so it can't go up or down. There is no A2x. There's just no forces in it because it's one-dimensionally falling. And then looking at our picture, we can see that A along the rope, A along the rope, and A along the rope have to be the same. So that means that A1x is equal to A3x is equal to A2y. Does that make sense?
Yes, thank you.
So, and we'll just call this A. Going back to our equations then, if we really just look at this center equation, we have M3, and I'm going to call AX3A, is equal to T2 minus T1 minus M3G sine of this. Now, T2, if I move this down so you can actually see it, M2A is equal to M2G minus T2. Solving this, move T2 over, move M2A over, I get M2G minus M2A. I can just plug that in here. And then T1 is obviously, so M1A is T1. All right, so I get M3A is equal to M2G minus M2A minus T1, which is M1A, minus M3G sine theta. And now I just want to combine like terms. So I can see that if I move M2A and M1A to the other side of the equation, what I get is I get M1 plus M2 plus M3A is equal to M2G minus M3G sine theta. Now, I'm going to rewrite that on the next slide. So M1 plus M2 plus M3A is equal to M2G minus M3G sine theta. Now, looking at this and looking at our system has a weight on 3 that's trying to pull it to the left. Our system has a weight on 2 that's trying to pull it down and pull 1 and 3 to the right. Those are the only 2 forces actually acting on it. And what we should see is that the sum of our m's times the net acceleration should equal those 2 forces. And is that what we see? Yes. Newton's law said that the sum of the masses times the net acceleration is equal to the sum of the forces. These are the only 2 forces in our system, really, that are acting. We can actually determine A by, since these are all the same, all these m's are the same. We were told that in the problem in part 5. You're told that all the masses are equal and they're 4 kilograms. That doesn't really matter, but A is if M1, M2, M3, this is M times G minus mg sine theta, but this is 3m. So if I divide by 3m, what I get is I get that A is G 1 minus sine theta over 3. All you do is cancel these. These both have a G in it, so I pulled one out. Now I said that this was at 20 degrees. So I can find A as 9. Why are you being such a pain? I think it's my hand that does that. Like palm over 3 times 1 minus sine 20. Okay, so putting that in our calculator, let me grab my calculator really fast. Um, 9.81 times 1 minus sine of 20 divided by 3 is 2.15. So our acceleration is 2.15.
Excuse me.
Yes, ma'am.
Would you please go 1 slide back?
To this one?
I don't know what happened to T1.
T1 is M1A. So I just,
You put it there. Okay, thank you.
yeah. Yeah. Okay. So once we got there, we have A. And then what I asked you is If it starts from rest and falls 5 meters, what is final V? Stop it. So if it starts from rest, that means V initial is 0. We want V final. Oh, and it falls 5 meters. M2 does. We want to know V final and we want to know T. So just looking at M2, A for M2 is still the same A. We can find V final from V final squared minus V initial squared is 2A X final minus X initial. You could also call these Y, doesn't matter. This is 5. This is 0. 2 times A is our 2.15 here. And V final squared. So take the square root of 2 times 2.15 times 5. Square root of that answer is 4.64. So V final is 4.64 meters per second. It's plus or minus because it's a square root, but you can just call it plus. And then to find the time, since you know V final is equal to V initial minus GT, this was 0, T is V final divided by G. In this case, oh, I'm stupid. Sorry, you guys. I'm in La La Land, plus AT. This is 0. We get that T is V final over A, which was 4.64 divided by 2.15. And that's going to be 2.16-ish seconds. That shouldn't be too hard. And that's all I want you to do. So you're going to make a free body diagram and give M1 A1X, M2 A or M1 A1Y. Same for mass 2, same for mass 3. Answer these questions and then solve for the acceleration and then solve for the final velocity if it falls from rest and drops 5 meters. So hopefully that makes sense. Let me know if anyone has any questions about that. Yes.
For number 4, for the last part, I said that if velocity is constant, all the accelerations would be 0 because the rope is stretchless. Is that correct?
Yeah. No, it's because constant
I didn't write
velocity
the
means
because part, but
that the acceleration isn't changing. Remember
Okay.
that the acceleration is the time rate of change of the velocity. So if
Mhm.
there's 0 acceleration or if the velocity isn't changing, then there's no acceleration anywhere. Those two things, starting from rest and constant velocity, you really need to know what that means. If you see those terms in a problem, they immediately imply A is 0 or V initial is 0. Okay. So hopefully that won't take you guys too long. And hopefully it's absolutely useful to at least most of you. If you've already got it down, great. It should only take 10 minutes to knock this out. But if you don't, I hope it's useful to you guys. Okay.
Professor, I have a quick question.
Sure.
For the Newton's equations given in from questions 1 to 3, is that just the M3 A3 of X and the M3 A of Y and so forth?
Yes.
Okay. Just want to make sure because I thought we had like a combined them to make a combined equation because that's the way I made it sound.
Not until you get down to here. When you're down here, I want a numeric value for the acceleration.
Right.
So you'll need to combine your equations above. That's what we're doing though, Sammy, is we're basically getting an equation for mass 1, getting an equation for mass 2, getting an equation for mass 3, and then substituting the equation for mass 1 and mass 2 into mass 3 and solving. That's what we always do with these. All right, so I'm going to put that away and go to today's lecture. Today's lecture is chapter 6, and I have to say it's deceptively easy. I don't know why, where, oh, there. It's deceptively easy because once you know what you're doing, it's it really is pretty fast and easy. You're essentially adding one new force to everything we did in chapter 5. But that new force is complicated. And so I'm going to stop sharing this and I'm going to start sharing my PowerPoint. So hopefully it's easier for you all to see. So let's talk about friction. Let's talk about a lot of stuff, actually. So we all know what friction is, I think. I think you all kind of have I mean, you're alive. You know that if you drag your feet on the ground, it slows you down and your feet will heat up. But imagine you're a scientist and you're trying to figure out what exactly causes friction. So you know that if you roll or slide something across the table, it stops. And that's due to friction. Friction basically stops things from sliding forever. And you want to come up with an experiment that tells you something useful about friction. So you need to model friction somehow. That is where our book gets us in trouble, because friction is super complicated. It really, really is. And we're going to take a really simple model that doesn't necessarily work. We're going to take the simplest model in the world. What you would do in an actual lab is you would basically create this series, this perturbation. You would find all these terms and try to figure out what each of the terms in the frictional force came from. We're not going to do that, as you'll see. There are 4 topics today: static friction, kinetic friction, and I'll explain the difference between those two. We're going to also have horizontal uniform circular motion, and I'll explain that, which leads us into curves. There should also be drag on here, but we'll talk about that when we get there. And hopefully you'll understand when we talk about drag why our friction model is so simple, because the drag model is not, and yet it's not the best model in the world either. So I want you all, if you're sitting at a desk, to do me a favor. I don't know if you can see my hand. I don't know. Well, you can just take both your hands, okay? So take both your hands, put them together, and try to push your hand, slide your hand over the other one. Don't push very hard. Give it an easy push where it doesn't quite slide yet. If your hands are really slippery, I guess it'll slide right away. If your hands are super dry, mine are kind of dry, you'll notice you have to push a little bit on it before it starts going. There's definitely a force that you have to push with a minimum force before it starts sliding, okay? That is static friction. It's, if you have, you know, this calculator in my hand, there's a certain amount of friction that's keeping it from sliding as I move the angle. And then eventually it's going to overcome that and slide off into my hand. That static friction is friction that keeps any motion at all from happening when you have an object on a rough, and by rough I just mean surface with friction. Now, there's also kinetic friction, and kinetic friction is the other type. Kinetic friction is when your car, you apply your brakes and your car slides. The tires on your car slide across the ground. Kinetic friction only affects an object in motion. Static friction only affects an object that's not moving. So they are 2 very different things. They are from the same result, but they are so vastly different in how we handle them that they are really actually totally different problems. We'll get to that right now, Magdalena. So how you envision friction is really kind of up to you. A lot of people imagine that there's a lot of little rough nooks and crannies on the bottom of an object and on the surface, and they kind of interlock and the frictions as it's like bouncing along that. But what it is actually intermolecular forces. Those of you in chemistry know this. There are electrons floating around in all these atoms between the two objects, and they're interacting with each other. Friction is when basically motion is turning into energy and being released as heat and light and all sorts of other things. Essentially, how heat and friction come together is that it's actually the intermolecular forces, and as the two collide, electrons are being sped up and given momentum in weird directions. And if you don't know, kinetic theory of gas, heat or temperature is directly related to the velocity of the electrons in the gas. So you're basically heating up the electrons by giving them energy, which is motion. We'll get to that after the first exam, but it's very complex. It's so crazy complex that we can't do it justice. So what are we supposed to do? If we can't, start talking about quantum and atoms and electrons and kinetic theory of gases and all that stuff, what do? Well, we make a really simple, dumb, and by dumb, I mean ultimately not very useful approximation of what the force of friction is. We put that into our model that we developed in chapter 5 as a force and try to answer what the acceleration will be when friction is present, or what the total net force on a system is when it's present. Some of you might be going, okay, I think I can make a good model. We have to understand that the model has to address a few things. It has to address static friction, being able to prevent an object from moving until you reach a break force, which means static friction has to be some variable force. Static friction always has to oppose the net acceleration. If the system had no friction, you have to oppose the acceleration it would have, which is a little difficult, and we'll talk about that. Kinetic friction has to deal with moving objects. So we're going to assume kinetic only is constant. Static friction isn't constant, it's variable. And that the kinetic friction, we're going to assume, always opposes whatever direction you're moving in. That's really important. That's the most important thing about friction. That leads to some problems when we don't know which way the object's supposed to go. How are we supposed to assume the correct direction for friction? And you might say, oh, well, that should be easy. It's not. It's actually not. You've got to draw friction on the free body diagram, but you may not know yet which way it's going to move, which means you're going to make a choice, and sometimes you're wrong. So friction's a pain. It's a real pain. Now, our very simple mathematical description, I think, makes sense to everybody. The normal force is proportional to friction. So we said that the normal force was how much an object pushes on another object. So the more that an object pushes on a surface, the greater the normal force. The greater the normal force, the greater the force of friction should be. And you can try that for yourself. This is a philosophical choice, but we're saying that it must be related, and basically it's the normal force times some coefficient. Now that coefficient we're assuming is constant. In reality, these things might not be true. You might have objects that actually have less friction when the normal force is greater. I don't know why that would be, but maybe you do. Maybe like a gas layer forms or something. You might have a variable coefficient maybe certain patches of ice are rougher than other patches, so that ice isn't actually frictionless, all that. But we're going to ignore all that. And what we're going to do is we're going to say that friction is just a coefficient times a normal force. And the more the normal force, the greater the friction. We have to apply a negative sign. And the negative sign is because we said that the static friction always opposes the acceleration, and the kinetic friction always opposes the direction of motion. So therefore, it's always negative. We're just going to throw a negative sign on there. That's going to get us in a little bit of trouble because when we draw a free body diagram, what does negative mean? We don't put negative signs on free body diagrams, right? We put them in the direction that's negative. So what this really means is it opposes the direction of motion. We'll get into that. And US, µS, and µk are coefficients, and how they're related, we'll talk about that. But let's just talk about static friction to begin with. So in the simplest example that you can have, you have a block, you're pushing on it with a force to the right, and there's some friction in this. Usually when people draw diagrams, they'll put like a rough pattern under the surface to indicate friction, just so you know. Give the free body diagram. So here's the thing. We know that this has a normal. So as before, we have normal, weight, tension, force, and now we're adding a fifth, force of friction. So we know it has a normal force, and we know it has a weight, which is mg. We're now going, okay, we did normal, we did weight. There's no tension, there's no ropes on this. There is a weird force that's pushing it to the right. And then we have a force of friction. Well, if A is to the right, which we're assuming it is because this force, then the force of friction has to be to the left. And we know that the force of friction is negative µs, where the negative µsn, where the negative implies that it opposes the force. That's why we drew it this way. But it has a magnitude of µsn. Okay, static friction now. Static friction means that nothing's moving. So if we write our equations, m1ax and m1ay, they're both going to equal 0. We're assuming x is along A and y is up. m1ax is f minus µsn. m1ay is n minus mg. Now look at this. Our force of friction is equal to our force if it's not moving yet. That should make sense. But we need to find the normal force now. And using y, we get that the normal force is mg. So this equation becomes F is µs mg. All I did was I solved this for n. Well, I solved this for n. And then I plugged n in here. And then I solved this for f. Okay. So I'll come back to that. What is the maximum force that can be applied such that it will not move to the right? So we got that F was µsn, and n was mg, and a was 0 for ax and ay. We want the maximum value this can be. Well, F is equal to, what did they say, 0.88? 0.88 times, so this is µsmg. I said that it was a 2 kilogram block and 9.81. So what do I get here? I get 0.88 times 2 times 9.81. 17.2656 newtons. Now, what is the maximum force we can apply to this block? This is the maximum force. Once we overcome this friction, it starts moving. So we're assuming in this problem that it's enough force that it's not moving yet, but an instant from now it will be. What if I apply a force? Oh my God. What if I apply a force of 17.26560000000001? If I apply that force, it starts moving to the right. If I apply a force of 17.2656 newtons, it doesn't move. If I apply a 2 Newton force, it doesn't move. These two questions right here, what is the maximum force? That it will not move to the right. What is the least force to begin it to move? We're assuming that this is the maximum and that any force, any incremental force beyond it, it suddenly starts sliding. If you put your hands together and see if, like, how much force, it's that break point right when it starts moving. That is the amount of force needed to overcome static friction. A second one, same 2 kilogram block, but now, yep. In fact, 265600001 would overcome it, Sam. Anything greater than this would overcome it. It's the break point, and that's what you need to understand. With static friction, all we have is a maximum force that you need to overcome to start moving. Anything less than that, it doesn't move. So here, let's go, I don't know why. Let's put it on a incline. Okay. Now, when we do it on the incline, we go back to this normal weight in the y was mg cos theta. And we're assuming that the weight in the x is down, so mg sine theta, as we've done for all of these. Which way do we put the static friction? Well, if I write the forces max and may, where these are my x and these are my y, and I'm going to assume that a is actually down the incline on this one, max would be mg sine theta. May would be n minus mg cos. There can be no acceleration in the y, so that equals 0. But I still have to put my friction, right? I have static friction. Where do I put it? I obviously put it in the x because it opposes the motion, and the only motion in this case we have is down the incline. So force of static friction is equal to negative mu Sn in the x direction. That means, since I chose a, well, let me actually not do that. I'm going to confuse people. A, let me choose to be up the incline. So this is negative. In order for A to be 0, which it has to be static, I can see that this has to have, max has to be the force of static friction minus mg sine theta, has to equal 0. Furthermore, I see that the force of static friction is equal to mg sine theta. And since the force of static friction is mu Sn, that gives me that. So mu Sn is equal to mg sine theta. What is n? Well, here, if I move that term over, I get that n is mg cos theta. So putting that together, mu s mg cos is equal to mg sine. The mg's cancel, and I get that mu is sine theta cos theta, which is tangent of theta. This is really important. Mu is the tangent of whatever my angle is on an inclined plane. That should tell you something kind of weird is going on here, but it's totally true. Now, we've got, if we go back, I'm going to add a new slide. So in this, I said, At the instant the block begins to move, we note that the force is 6.1. That means that 6.1, so let's look at this. It says that a 2 kilogram block rests on a level surface, and we begin applying a force on it. So right now, at the start, to explain this a little bit better, at the start, this block is sitting there and it's not sliding down at all. It's not moving. Then we start applying a force to it. So we start pushing it, let's say with our finger, with some force. And eventually that force is enough to overcome the static friction. Okay. So what I now have to do is there is now a force on here. If I draw this normal mg cos theta, mg sine theta force, which way is my static friction going to go? That becomes a problem. Here now, so if we go back to this problem and look at this, I forgot to include the force, so that's what I'm fixing right now. So let me do this really fast. With the force, I'm assuming A is going to be up, X and Y. Then friction has to oppose that force. M-A-Y, M-A-X. M-A-Y is 0, it can't leave the surface, N minus mg cos. And that gives us that N is equal to mg cos. M-A-X, assuming A is going to the right, is F minus mg sine theta minus force of friction. Now, right before it moves, if we assume right before it moves, there was no acceleration in the X, we get F minus mg sine theta minus F of friction is 0. What did I want to know? What is the coefficient? So this is F minus mg sine theta mu Sn, and I want to solve for mu s. Move that over. Mu Sn is F minus mg sine theta. Mu s is F minus mg sine theta divided by n, but I have n right there, mg cos theta. So mu s is F divided by mg cos theta minus tan theta. I can put numbers in here. So F, I said in the problem, was 6.1. M was 2 kilograms. F 6.1 newtons. And what was our angle? 20. Did I not even give? I am so sorry. Let's assume that this thing has an angle of 20 degrees. I might have screwed this up. I got sidetracked on something. If that were the case, will this even work? 6.1 divided by 2 times 9.81 times cosine of 20 minus tan of 20. Okay, so that's actually not going to work. Let me backtrack for a minute. I realized I was thinking I was on a surface. You guys can yell at me and tell me to stop when I screw up stuff. I don't want to draw. So let's go back to this. I got ahead of myself.
Professor, quick question.
Yeah.
With the U S of n over sine of theta and cosine of theta, how did you get that? Because I was a bit lost on that.
I'm gonna come back to it right now. I realized I was thinking I was on an incline and I'm not. So sorry, gonna reset this for a minute and then we'll talk about inclines. we're on a level surface. So I don't know how I managed to, too many problems already this morning. So this is, we're applying a force. There's a normal force. There's a weight. And we're going to assume that A is 0, but it goes that way. We're assuming A is 0 because it's not moving. So when we draw this, you still draw the normal, you still draw mg. We're applying a force of 6.1 newtons, and that's the amount of force right before this block starts to slide to the right. And then we need to know what is the coefficient of static friction. So if A is going to the right, we note that the force of friction has to go left, which is minus mu n, little s. This is y, this is x. So now writing these M-A-Y and M-A-X, and I always write them backwards, just something I do. It's 0. M-A-X is F positive minus mu n. This is not a minus though. You can think of it as a magnitude. So that's minus mu n. That is also 0 because we are doing static friction, and static means A and B are both 0. All right, so from this, from MAY, we see that N is mg. From MAX, we see that F is mu Sn, which is mu S mg. And we want to find mu S. So mu S is F over mg. If F is 6.1, M is 2, and this is 9.81, we get 6.1 divided by 2 times 9.81. I get 0.31. 0.31. Now notice something though. If this is force divided by mg, mu s has no units. It's strictly a ratio. In fact, we'll see what the ratio is. We've already seen it, but I'll come back to it. So the main takeaway here is that the force of friction is mu times n, either s or k. N usually comes from the y component of the forces, of the sum of the forces. And we always put a negative sign because it always opposes whichever direction the acceleration would be if there were no friction. So a few other things about static friction and kinetic friction. This is super important. So let's say I'm applying a force to this block and I start at 0 and I move and I move and I move and I move until I get to 6.1 newtons. Once I get to 6.1 newtons, the block begins sliding to the right. And friction actually drops, okay? It's actually easier to slide something on a frictional surface than to get it started moving. Yeah, I'll talk about that in a minute, Sammy. Okay, so if you've ever pushed a car or pushed really anything heavy, you should know that getting it moving is a lot harder than keeping it moving once it's sliding. The reason for that is the kinetic friction, once it's already moving, is actually much less than the static friction. But this little chart, which is in your book, actually really nicely illustrates the difference between static and kinetic friction. Static friction opposes the force until the force overcomes it. And once the force overcomes the static friction, the object begins to move. Once it's moving, friction drops, but stays mostly constant in kinetic friction. The coefficient of static friction has to be greater than the coefficient of kinetic. The reason why is if you're pushing something And once it breaks free, all of a sudden you have to overcome more friction, a greater force of friction, then that kinetic friction would still be static, right? It still wouldn't let you move. If kinetic friction were greater, it wouldn't move even after it broke loose because it would still have to overcome the kinetic friction force. So kinetic friction always is less than static. It's a weird physical phenomena, but here's the plain one, Sammy, that I'm going to go over that I was thinking I was on. And I'm sorry, you guys, I kind of autopilot sometimes. I know what I'm going to next, and I jump to the inclined plane. So here on an inclined plane with friction, so there's a mass, and this has friction. This is some m. This has friction with mu s is 0.50. So you set it on this rough incline, which is at 20 degrees. And then you want to know, will it slide? So doing the turn on its side thing, getting the forces, normal. Remember, weight in the y is mg cos. Weight in the x down the incline is mg sine. And now I'm going to assume that a is up the incline and x and y are positive like so. Now, this is what I was trying to get at earlier. We know that the y is 0 because it can't leave the surface. But the x also has to be 0 because it's static. And we only have one force on our diagram right now because we haven't put friction on here. So we need, if a is going to the right, this is negative mg sine, but we need this to equal 0. So the force of friction has to be to the right. We can see that, right? In order for the forces to be 0, there has to be a force of friction to the right, mg sine to the left. However, that's hard to, like, just think about it. If you set something on an edge, okay, maybe intuitively you go, oh yeah, the friction points up the incline because it's keeping it from sliding down. We're going to see in a minute that it's not that simple when you get other forces involved. But for now, it's pretty simple to see that the force of friction must equal mg sine theta. And we know the magnitude of the force of friction is mu Sn. So free body diagram, and mg cos, we're on an incline. Mg sine, force of friction, which is mu Sn. And we know that we're choosing A up. It doesn't really matter though, y and x. So our equations, m ax, m ay, 0, 0, n minus mg cos theta, force of friction minus mg sine theta. This implies n is mg cos. This implies, since this is mu Sn, that mu s is equal to mg sine divided by n. If I plug in for n mg cos, I get that mu s is mg sine theta over mg cos theta, and mu s is therefore tangent of theta. And this becomes a pretty weird question. We can do it two ways. Does it slide? We can figure this out one of two ways. We could ask, is the force of friction greater than or equal to mg sine theta? What that's saying is, if the force of friction is greater than the weight, it can't slide to the left. Or alternatively, you could think of it as, if mg sine theta is greater than the force of friction, it slides. It does not slide. Whichever way you want to see that. Okay. So you could find the force of friction in mg sine. We know that m was 2, 20. So M was 2, angle was 20. And mu S was 0.5. Yep, 0.5. So let's find these, 0.5. Force of friction was mu S mg cos theta. That is 0.5 times 2 times 9.81 times cosine of 20, and I get 9.218. Okay. And then what is mg sine? 2 times 9.81 times sine of 20, 6.71. It can't slide. 6.71. Stop doing whatever you're doing. 6.71 is not greater than the force of friction. The force of friction is 0.5 times 2 times 9.81 times cosine of 20. The thing does not slide. It can't slide. Another way to look at it is mu s of tan of theta, tan of 20, would be 0.36. What angle would it have to be for it to slide? We could actually find that by doing arctan of mu s. And arctan of 0.5 is 26.56 degrees. Now, that's a little weird to think about, but basically, it would have to be at least 26.56 degrees in order to slide. We can look at that. So what happens when our forces are, if our angle is 26.56 degrees, what is our force of friction? Our force of friction was mu s mg cos theta, and our weight in the x was mg sine theta. So what is this? 0.5 to 9.81 cos of 26.56 to 9.81 sine 26.56. So 0.5 times 2 is 1. 9.81 times cosine of 26.56 is 8.77 newtons, and 2 times 9.81 cosine sine of 26.56 is 8.77. Okay, so there's a very huge important lesson here. In this particular problem, it cannot slide because the force of kinetic friction is greater than the weight. But there's an even more important thing here. Friction can't make it accelerate up, okay? So this, if I go back and look at, I say that MAX is equal to 0 is equal to force of friction minus mg sine theta. This becomes mu mg cos theta minus mg sine. And when we did it here, we got that this was 9.218 newtons and that this was 6.71 newtons. So MAX would be what, 2.5-ish, 2.5-ish, right? Meaning it would go up the incline. That doesn't happen. You have to be careful with friction. You have to understand that when you do friction, friction can't cause acceleration. Friction can stop acceleration, but it can't cause acceleration, which is so weird. And I understand it's confusing as all heck. So we're
Professor, I have a quick question.
yes.
On the full body diagram for this problem, you have the force of friction going the same way as the acceleration is going. Is that not allowed? Because shouldn't it be opposing each other?
No. I assumed when you have static friction, it really doesn't matter, to be honest. Let's do it the other way.
Wait, then so when should it, what should it be opposing then, the force of friction? Should it be opposing the A or should it be opposing the mg sin of theta?
Should
Because
be opposing. Imagine we have no friction. Which way does this block go? This
It'd be
block, it slides down, right?
right.
So I know that my force of friction has to oppose that. And that's it. The best way I can tell you to do it is assume that the system has no friction and look at which way it would go. And
But
then,
doesn't the A represent the way it's supposed to go though?
no, the A represents which way I'm calling positive. And unfortunately, Wiley loves to go up the incline as positive A. So I left it at that. That's how Wiley does it. How I would do this problem is I would assume A was down. So let's do that. Let's assume A is down the plane. This is actually kind of important for all of you. So mg sine theta and force of friction. So let's do it for A that way, and let's do it for A this way. Okay, so it's not negative, Lucas. Force of friction is not negative mu Sn. It's mu Sn. The negative sign in the force of friction implies that it has to oppose the acceleration. It's not negative if you haven't assigned it. So in a weird way, maybe this would make more sense to try and show it. If we're assuming that this is the only force acting, then you could say that force of friction is negative of that. Yeah, you don't worry about the negative sign. Forget the negative sign is even on there. Force of friction is mu Sn or mu Kn. So in this case, Sammy, we get that MAX this is positive, mg sine theta minus mu Sn. In this case, mg sine and force of friction, we get MA is force of friction, or mu S, I guess, since I called it that in the last equation. Mu Sn minus mg sine theta. But since they both equal 0, it doesn't matter. We're going to see that it does matter in a second. But does that make sense, Sammy? They're the same exact equation.
Wait,
I guess I could put, yeah, they're the same exact equation.
but isn't that, wait, how are they exactly the same? Because I know, because we're subtracting the US of n by the mg sin of n, and then the other one's the opposite of that. So
They're
isn't that not?
because they both equal 0.
Oh,
Yep. The point here is that you're going to choose A, Sammy. This is actually really, really fundamental. The reason why I have you draw A on your free body diagrams is you're going to choose a direction for A to be positive. What if this wasn't 0? What if I had no clue whether it was positive or negative? If it came out negative, I would know that the acceleration is therefore opposite the direction I chose. Signs are vectors here. Everything here is a vector. So a sign has a definite meaning beyond subtracting a number. It definitely means a direction. And if the A ends up negative, then that's your direction. But you get to choose whether A is up or down. It's confusing, Sammy. I think it's confusing for you guys because look, here's a question I have for you, Sammy. And I don't mean to sound irritated. You know that you can choose Y and X to be this way, but there's nothing in the world that says that you can't choose that to be true, right? And the problem is that much like when we have an object in free fall, You can choose the acceleration to be negative g. What does that mean though? If this object is falling, when you're saying negative g, what does negative mean? That's my point here. You don't realize it, but you're assuming that a is positive up in free fall. And you're calling the acceleration down. If we do free fall this way, doing free fall as a free body diagram, a ball falling, you would draw mg. You need to choose a direction for a. So which way do you want a to be, Sammy? Do you want a to be up? Do you want a to be down?
It would be up.
No, it doesn't have to be. It's totally your choice. You could flip a coin.
I'm used to it being up, so I'm just gonna assume it's up.
If it's up, what that means is you write ma is equal to negative mg.
Right.
But maybe you don't care and you just want to say it's down. If it's down, then ma is equal to mg. Those are exactly equivalent. Both of us are getting the same exact direction for the acceleration, right?
Right.
We're both getting that it's down. So you can choose a direction. And the reason why in chapter 5, I'm telling you to choose one is to set up friction. When we have friction, we really have to look at how the system's moving and choose a direction for friction. And sometimes that's my point is exactly, you're right. It is confusing. It's not straight up where you can just say, okay, A is going to be up the incline every time. That doesn't work. That in fact makes things much harder. Let's do this problem right here, where we now have a block. And this is where I deliberately want this to be confusing. We're pulling this block up the incline with a 2 Newton force. What does the free body diagram look like on this? There's a force up, there's a weight down, mg sine, there's a normal force, and there is a weight mg cos. And now here's my question to anyone, not Sammy, anyone. There's static friction in this. So we know it's not moving. But how do we find the direction on the free body diagram? Where do we put the static friction on this? How do we know? And it's not a simple question always. How do we know which way we're supposed to put the force of static friction? You can do one of two things. You can assume right now that there would be an acceleration without the static friction. So find that acceleration and then put the vector for the static friction in the opposite direction. Or you could just write max is force minus mg sine plus the force of static friction. And you know that's got to be 0 because it's static. And then you could find that the force of static friction is mg sine minus f. Here, we know this was 9.81 sine 20, and I said that this force was a 2 Newton force. So is it going to be positive or negative? 2 times 9.81 times sine of 20 is 6.71. 6.71 minus 2 is 4.71. Now it's positive. What does that mean? Well, in order for this to be true, I had to choose A was that way. I forgot to write A on there, but I had to choose that. That means that if the force of static friction's positive, it's in the positive direction. That's why you've got to draw A. Had I wrote A that way, this would be mg sine minus f plus force of static friction. It would have given me a negative number, which would have told me that the force of static friction pointed to the right. But it's confusing because you don't always know. And sometimes you'll make a mistake and assume static friction points in one direction and be wrong. And it messes up everything. I guess I should put newtons here too. So the good thing is this stuff is really only confusing because static friction is always confusing. You don't know which way the direction goes yet. You're supposed to put the direction or the force of friction opposite the direction it's traveling. And that's a huge pain. I almost never ask about static friction. You do have some penguin problems. And why I call them penguin problems is they're a cute little penguin in a boat that you'll see in the, or in a box. And the penguin got static friction to keep it from moving for homework. Kinetic friction, much simpler, much easier. Why is kinetic friction easier? Because it always opposes the motion and it only applies when the system is in motion. So you're going to know what direction it's going in, and you're going to know that the force of friction has to be opposite that. And that's helpful, okay? It always opposes here. So let's talk about this. A block is moving to the right, just a block. It's flying to the right with 10 meters per second of velocity. And there's some friction on the surface that it's sliding on. We want it to slide to a stop. So it's eventually going to slide through all of this and come to rest at some distance delta x away. Now, how do we solve this? Well, you might already be thinking, oh, I can find delta x from, from v final squared minus v initial squared is 2a times delta x. And I know that v final will be 0 because it comes to a rest, but, and I know v initial, but I don't know a. Well, how would we find a? Free body diagram. Free body diagram, normal force up, mg down because it's on a flat surface. It, I'm going to assume that if v is moving that way, that the acceleration is also that way. Now, there is friction. Where do I put the force of friction? It always opposes the motion. So that means that it's in the opposite direction of the velocity or acceleration. Force of kinetic friction. The force of kinetic friction has a magnitude mu, k, n. I'm going to probably start leaving off the q or leaving off the k and just writing mu n. Okay, so what do I get for the equations of motion here? M a x, a is positive, therefore the force is negative, and I know that it's got mu k n. M a y is 0, it can't leave the surface, n minus mg, which implies n is mg. That implies that max is negative mu k mg. All I did was this became max is negative mu k n, and I substituted for n mg. What is my acceleration? Well, the m's go away, and I get that a is mu g with a negative sign. Mu was 0.3, negative sign 9.81. So what do I get? Negative 0.3 times 9.81 is 2.943. Now that I have that, I can actually plug that in. Go. I can actually, I don't know what that just did. I get that solving for delta x is negative v naught squared over 2a, negative 10 meters per second over 2 times a is negative 2.94, and that gives me 100 divided by 2 times 2.94, about 17 meters. So let's go through this a little more slowly. What did I do? I started off with M sliding to the right. My free body diagram, I check for normal force, weight, tensions, forces, and force of friction. I know that there is friction because I was given that mu equals 0.3. Okay. And I was told that the initial velocity was 10 meters per second. So just drawing the forces on this, there is a normal because it's on a surface. There is a weight, mg, because it's on a level surface. There is no other force on this right now. It is going to the right. The only force acting is the force of friction opposing the motion to the right. That's it. Once I find A, I'm going to use it in this equation to find how long it takes to stop by finding delta x is negative v naught squared over 2a. This is 0 because it stops. And from that, I wrote max was negative because A is to the right and the force of friction is to the left, mu n. So here you see why it's always negative. It opposes that. MAY is 0, can't leave the surface, n minus mg, which gives me that n is mg. So A is negative mu n over m. All I did was I put the divide by m. And negative mu over m times mg, these cancel. A is negative mu times g, negative 0.3 times 9.81. Plug that in there, plug 10 in, and you've got the answer. That's it. It's much easier to do kinetic friction. It can get hard though, and we'll see a few things where it does get a little harder. So if we assume that it's on a inclined plane, 20 degrees like we did with the other one. No, Lucas, you always oppose. So I personally hate that your book, that any physics book puts a negative in there, when that negative implies that it's opposite the direction of motion. This math, okay, I really need to make sure you guys understand this. So here's the question to you. If the block's traveling to the right, which way does the force of friction go? Negative. But what does negative mean? It means in the opposite direction of the velocity. That's what it means. Whatever direction it's traveling in, if it's traveling on a frictional surface, the negative implies that the vector points opposite to the vector for the velocity. Does that make sense, Lucas? Go ahead.
Well, just because you like put a negative number in the accelerate, because you have acceleration equals negative 0.3.
I'm assuming that A is going that way, right? So when I write my Newton's equation, MA is negative force of friction. I do not write negative mu n9. This is not correct. It's
No.
negative mu n.
Yeah.
That's where they got that negative from, in that equation. That negative sign happens in that equation because they're always assuming that the velocity direction is positive. But that doesn't have to be the case. And you know already a case when that's not true. How about this? You fire an object into the air and it comes back down, right? So you're already assuming that A was positive up, and that's how we got negative G to be down, right? And now the velocity is also down. So if for some reason you had, like, it was in some wood thing where it went up and it came back down and there was friction on either side, which way does the friction point? Well, it always points opposite the direction of travel. But you have to be really careful on what you're calling positive and negative. So that negative sign is, it's absolutely better to just think of force of friction is mu n. The sign just depends on where you put it. Does that make sense?
Okay. So if you were asked to find the like force of friction, you don't necessarily have to put a negative. The negative just says it's opposite of acceleration.
Just like we didn't have to put a negative G. The reason we put negative G was because we were assuming Y was up. The negative sign is if you're assuming that the friction is opposite the velocity and the velocity is in the positive direction. But that's not always the case. And that's what I'm trying to get through to you guys. And we're going to see that right now. So this one, if it rests on here and there's kinetic friction somewhere here, okay? If the block moves with constant velocity, what is the coefficient of friction? Now, we don't know if it's going up or down, right? But there's no forces on it. So if it's moving up or down, it really doesn't matter. We're going to see that right now. So on this guy, let's assume that he's moving with, I wish that thing. Let's assume that it's moving with constant velocity up the plane. First, so it's going V constant up the plane. Let's take A to be positive up the plane. If we draw our free body diagram and it's on a plane, mg cos, weight mg sine, and now because we're assuming it's moving that way with constant velocity, force of kinetic friction is here. Let's do this one. What if it's moving down, right? And therefore, n mg cos. Which way does friction point? To the right, right? So let's look at these x equations. For this one, I get that max is equal to mg sine theta, I'm sorry, minus mg sine theta minus mu n. may is n minus mg cos theta. That's because we're assuming that the acceleration is positive in that direction. Both the forces on it are negative and down the plane. What's going to happen? It's going to slow down and stop, right? It's eventually going to stop. Now, as it slides down, what do we get? Let's assume that A is still positive up the slope, but B is down the slope. So MA is equal to force of friction minus mg sine theta. MAX, I should say. Here, I'm assuming that these guys are, well, hang on. I'll get to that in a minute. MAY is still n minus mg cos. But remember that everything's constant, so this is 0, right? Can this happen? This can't happen because you would get a negative force in the x. It cannot happen. that is one of the things that you need to make sure you always remember. This can happen. These two could be equal to 0 as long as force of friction is mg sine theta. But that top one can't happen. So we need to always be careful with friction. Friction's not as cut and dried as you think. Sometimes it's that you set up a problem wrong or you make a bad assumption, but that can't happen. And I hope you guys see that that can't happen. MAX cannot equal negative mg sine theta minus mu n. It would end up saying that it can't be moving with constant velocity, which is fine, but it can't be 0. All right, so anyway, enough with that one. This one is actually kind of fun. If you have a mass on an incline and you have a mass hanging, which is kind of what we did in the quiz today, the masses are equal. Now, which way is this system going to move? Well, we don't know. I'm going to assume that for the first time, this is what's hard, and this is actually really hard. If I assume that they're going to move up, and I'm going to call this 1 and 2 even though they're equal, mass 1 is moving up the incline and mass 2 is dropping, I have tension, normal force on 1, which is mg m1g cos, and I have a weight m1g sine theta, and because it's going that way, I need to make my friction opposite. I hope that makes sense. For 2, I would have m2g and tension, and I'm saying it's accelerating down. So this is acceleration, this is acceleration. I get m1ax, m1a1y. This is T minus m1g sine minus force of friction. So it's the same thing as if we were doing it without friction. We just add a friction force opposite the direction of the acceleration. N1 minus mg cos theta is 0. This one is m2a is m2g minus t. Plugging t is m2g minus m2a into this equation, and assuming that a1x is equal to a2, call this a2, m1a is equal to m2g minus m2a minus m1g sine minus force of friction, which is mu n1, right? Remember that this is mu n, but it's for the first mass. Doing that, move the a's to the same side, m1 plus m2 times a is equal to m2g minus m1g sine minus mu m1g cos. And you can plug these numbers in to get A. So M2, they're both 3. So 3 times 9.81 is 29.43 minus 3 times 9.81 times sine of 20, 10.056 or 0656 minus 0.3 times 3 times 9.81 times cosine of 20, 8.29. It's 30. Sorry. You're right. I'm done. Let's get rid of that. I was still thinking it was 20. I did this carefully for a reason. 3 times 9.81 times sine of 35 is 16.8. 16.88. What is mu 0.3 times 3 times 9.81 times cosine of 35 is 7.232 something. So this ends up being plus 16.8. And then 29.43 minus this answer, 5.318 newtons. Now remember that this is 3 plus 3, so 6. So A is equal to 5.318 divided by 2m, which is 318 divided by 6, 0.89 meters per second squared. Okay. Got it, Hamid. So that's our acceleration. Here's the question I have for you. What if I wanted it to go the other way? What if I messed up and I put it the other way? How would I know what?
Excuse me.
Yes, sir.
So in this example, you assume that the box on the plane goes up, right?
Mhm.
Why? Why did you do that?
Because I assumed that 2 was going to fall, but I have no way of knowing that that's true. It worked out because I got a positive acceleration. The fact that my acceleration was positive told me that I was right. And that's what we're going to see right here. So what happens if we went the other way?
So we can do it in other way. If we get the negative numbers, it means that we were wrong.
Right, and I'm going to show you that right now. Sammy, did you get everything you need off this, Sammy? You mean this one? This one right here, Sammy? All right. Yeah. I just plugged in numbers, 0.3, M1 and M2 are both 3, G is 9.81, sine of theta 35. Let me know when you're done with that. Because there's 2 of them, M1 plus M2. Does that make sense, Sam? No, 2 masses. So I'm going to go to what happens when you choose the other way. So what happens when we choose wrong? And how do you know right away that you've chosen wrong? So back to, for number 1, there's a normal and an M1G cos. Remember that now we're choosing A to be to the right or to the left and A to be up. So I'm going to choose A to be that way. This is still mg sine. There's still a tension, but now the force of friction opposes that. And for 2, still m2g, but now A is up and tension is up. So now, here we go. So for number 1, we have M1A, I'm just going to call it A, is equal to M1G sine theta minus T minus force of friction. M1AY is N minus M1G cos. We know that that is 0. So this is N is equal to M1G cos theta. For this guy, M2A is equal to T minus M2G, which means that T is M2A plus M2G. Plugging it in here, I'm just going to plug these guys in. Mg sine theta minus M2A minus M2G minus mu M1G cos theta, and that's all got to equal M1A. Or moving that over, M1 plus M2 A is equal to M1G sine theta minus M2G minus mu M1G cos. And plugging numbers in now, I would get 3 times 9.81 times sine of 35 is 16.88. M2G is 3 times 9.81, 29.43. And you can already see that we're in trouble. 0.3 times 3 times 9.81 times cosine of 35 is 7.23. So Hamed especially, you can see here that we get a negative. The acceleration is negative. In fact, the acceleration is way too big and negative. It's 29.43 plus 7.23 minus 16.88 divided by 6 again. It's like 3.29. Now, does that mean it's wrong? No, not necessarily. In this case, it definitely is because, well, no, actually, I take that back. It's always wrong. It's wrong because once we realize the acceleration's in the wrong direction, we realize that our velocity, well, okay, I guess it's not always wrong. If I gave you a question where I like started it, sent it down the slope with some initial velocity, this would give you the acceleration up the slope, so how it slows down and then goes the other way. But yeah, in general, on an exam, what I would do, well, you're going to have to refigure it. If you just change directions, you're going to have to recalculate it because your friction has a different sign on it and your tension changes. Your tension equation changes. It's not that simple. So if
So
you
in
start
the exam, in the exam or in solving any question,
I just mean like
you-
on Wiley. If you're doing this on Wiley and you choose wrong, so a lot of times what happens is students will ask me like, oh, I'm getting a negative sign and I don't know why. The reason why is you chose the acceleration in the wrong direction.
Mhm.
If you get a negative sign for the acceleration, go back and rework the problem with the acceleration the other way.
yeah,
It's the best thing to do. It's just to check yourself that you don't have something weird going on. Unless, and in my exam problems, I will give you the direction of the acceleration and the velocity. So I'll tell you like, hey, take the acceleration to be down the incline or take it to be up the incline or take it wherever. But Wiley doesn't always tell you that. Some of the problems you'll be working on, it's like a toss-up, which way you should decide it's going to go. Or you just don't know at all. You don't know which way it's going to go. And that's what I wanted. I want to show
is
you.
it possible?
What's
Excuse
that?
me, is it possible that the acceleration is negative? For example, the acceleration is negative because, for example, the box on the inclined plane goes down, but the acceleration tries to stop the box.
Right. It's only negative if it's traveling down the plane. Okay. So what I don't want you to do is assume, let's assume this is whatever this is, 3.3-ish. This is negative 3.3 meters per second squared. That's what A here would be. Don't assume that that's going to make it go the other way. All that's going to do is stop it from going down. Once it hits 0, it's going to start going the other way. So basically traveling down the incline, the acceleration for the system is negative 3.3. Once it starts traveling up the incline, the acceleration is 0.89 up the incline.
Oh, okay.
Does
Thank you.
that make sense?
Yeah, thank you. Thank you.
Yeah, you're welcome. You don't, Sammy. That's kind of the problem. That's why I'm illustrating this, is you can end up, I would say that if you end up with a negative acceleration, whenever you're doing friction, if you don't know the velocity, right? If you have no idea which way it's going to go, So if I just gave you this problem right here and I didn't tell you A at all, so like this one, a 2 kilogram block is on an inclined plane at 40 degrees. Coefficient of kinetic friction is 0.9. What is the acceleration? I didn't tell you which way it's going, and it's kinetic, so we have to assume that it's moving in one direction or the other. We don't know. I will say this, though, that you know that it can't be accelerated up a plane by friction. This cannot happen. You cannot have a block sitting on a friction surface and suddenly be sent upward by friction. We all know that doesn't happen, right? So in this case, you have to know, you just have to know that this is implying that it must be going down and the friction must be up. So there must be mg sine, and that the acceleration, well, it's again the same problem that we just had. It could have an acceleration up and an acceleration down. When it's going up, it would be minus g sine theta minus mu g cos theta. And going down, it would be g sine theta minus mu g cos theta. I don't know what the heck you're talking about, Sammy. T following which part of it here? Yeah, T would also be flipped. So, well, no, T wouldn't be flipped, but the sign would be flipped. What I'm saying, overall, Sammy, all I'm saying, long and short of it is, if you are doing this with friction and you have no idea whether it's going up or going down, right? We have no idea. In this problem could be a Wiley problem, and Wiley doesn't tell you if it's going up or going down. But you know it's moving. You just have to pick one. You have to pick one, and you're going to get a number. And if your number is wrong, it's not as simple as flipping the sign. It's more than that, because the friction also flips. The friction always opposes which way it's traveling. And this is just a caution on that you don't know. So if you get a negative sign, I would suggest redo the problem with A going the opposite way. What's unfortunate is that if you don't know the velocity, you're in trouble. And in real life, you would know the velocity. But in these book problems, you're not always given the velocity. So it's really just a question of what do you know. Here's another complication on that. What about this one? Now, what would you do? This is a what would you do? You have two inclines, two masses connected by a pulley, right? And you're not told which way they're going. Call this one, call this two. But they're moving. How do you know which way they're moving? Right? Is it possible that it can't move one way or the other? So again, you just have to pick. And here we would have N1, M1G cos. This is 1. So to the right is M1G sine theta. There's a tension between them. They're connected by a rope. This is 2, N2. Now note something really important here. Cos theta 2, this is cos theta 1. So, oh yeah, sorry, ignore this. I don't know why I said that. Right. It doesn't matter though. M2G sine theta and a tension. And now we have a problem because we have two frictions and they're different. Both of them have friction. But here's the lesson right here. Sammy, Lucas, everyone. You have to pick one. And once you pick which way you think this thing's going, the friction has to oppose it. So I'm looking at this and let's say that these two masses are the same. So mass 1 is equal to mass 2 is equal to 3 kilograms. I forgot to write that on there. If they're the same, how do you know which way they're going to go? You don't. You have no clue. Okay. All you can do is start solving it, which totally sucks. I admit that it totally sucks. You could kind of shortcut it. You could figure out what the acceleration would be without the friction, but in this case, you have two of them. So let's say that I just decide it's going to go like this, right? Then my acceleration is to the left for both of these guys. I can write my equations as m1a1y is n1 minus m1g cos theta 1, m1a1x t. If it's going that way, force of friction 1, force of friction 2. They both go opposite the acceleration. So this would be m1g sine theta minus t minus force of friction 1. m2a2y is n2 minus m2g cos theta 2. m2a2x is m2, nope, t minus m2g sine theta 2, theta 1 minus force of friction 2. Yeah, I'm not sure what I did there. These just give us that N1 and N2 are those. We already know that. We know that the force of friction 1, the force of friction 2 is mu1 m1g cos theta 1, mu2 m2g cos theta 2. A1x is equal to A1y, or A2x. I'm just going to call these A. Let's solve this right in the middle. So I don't need these equations anymore, but I need these two. And I know that M1A and M2A is equal to M1G sine, I'm going to show you a fast way to do this, minus force of friction 1 and T minus M2G sine theta 2 minus force of friction 2. Now, doing this a very fast way, instead of doing substitution, just write them and add them together. Okay, I'm going to add them up here. M1 plus M2 times A is equal to, the T's cancel, I get is equal to M1G sine theta 1 minus F, force of friction 1 minus force of friction 2 minus M2G sine theta 2. And now, did we do it right? 0.4 and 0.25. Get those right. 45 and 30. And M was 3 degrees or 3 kilograms. Yep, 3. All right, so just plugging these numbers in here. M1G sine theta 1 is 3 times 9.81 times sine of 45. That's 20.81. F1 and F2. F1 is 0.4 times 3 times 9.8 times sine of 45, which is 8.324. And this is 0.25 times 3 times 9.81 times. Oh, wait, whoops, that's wrong. Whoops, that's wrong. I had a sign in there. 0.4 times 3 times 9.81 times cosine of 45 is 8.324. 324 and 0.25 times 3 times 9.81 times sine of 30 gives me 3.68, let's call it. And finally, M2G, 3 times 9.81 times sine of 30 is 14.75. So this is 14.715. This altogether is 11.9, 12.04. And so we can see that this is going to end up being -6-ish. So they're not going that way. We could redo this whole thing by looking at this and simply switching our A's and switching our, so A, and this becomes force of friction 1, and this becomes force of friction 2. And doing all of that, M1A1 would be completely different. And I'm going to leave those because those are still valid, but this is all going to be different. What were you saying? Quick question, why do we no longer need in the original? Because what they give us is they give us that the normal force is equal to M1G cos. So we don't need them other than to know that. And you'll find that you're pretty quickly going to just get used to not even bothering with it. So this is M2G sine theta 2 minus T minus force of friction 2. That's from here. This one would be T minus M1G sine theta 1 minus force of friction 1. Let's write this as A and write that one up above it, M2G sine theta 2 minus T minus force of friction 2. That goes away, and I'm left with M1 plus M2 times A is equal, I'm adding these two, is equal to M2G sine theta 2 minus M1G sine theta 1 minus force of friction 1 minus force of friction 2. I know those are 12. These two are minus 12. This is 3 times 9.81 times 3 times 9.81 times sine of 45 is 20.8, right? 20.8. And 3 times 9.81 times sine of 30 is 14. Huh. Did I do something stupid here? 14.715. Yeah. So in this case, it can't actually go either way. If it starts to go down, it's going to be pulled. If it starts to go down to the right, down to the left, it's going to have a negative acceleration. If it starts to go down to the right, it's going to have a negative acceleration. It cannot move. That is a huge, huge pain. And it's easy to end up in trouble. So what do? Well, you make sure that you're given the velocity, whether the velocity is going to the left or the right. In this case, I didn't give it to you. Wiley might not give it to you. Anyway, I just wanted to show you these ones that are traps, basically. This is a trap. It doesn't work because the numbers, basically the force of friction is enough to overcome, or it's too much to overcome the force of friction. So just so you know. And we'll do some friction in the homework problems, try them. We'll cover them on Thursday. Ones that are straightforward. I wanted you to show you these ones that are a trap. There's a couple in your book that are pretty easy and straightforward. I want to talk really fast about some fun stuff. And since we're almost done, the rest of this stuff, the rest of this chapter will not be on the exam, but it's worth knowing. So uniform circular motion, we already talked about it before. We talked about it like twice, but we kept assuming that it was going in basically a horizontal circle. Remember that we had this A rad that pointed inward, the velocity was tangential, and you got this period, A rad V is constant. Okay, but what happens if instead we're going up and down and we have some G? So we have another acceleration that we have to include, and that's the force of gravity. What are we supposed to do? So these are variously called Ferris wheel problems. If you don't know what a Ferris wheel is one of those rides with little seats and it rotates around. So we're going to assume that it's going at constant velocity around. We're further going to assume that that's clockwise or counterclockwise. So it has some, at every position, some constant V. But what we want to know is if you're sitting here, what does your acceleration look like? And vice versa when you're at the bottom. So to draw at the top your free body diagram, you're sitting on a seat, so you have a normal force and you have a weight. You always have these two, right? So do we have a tension? No. Do we have some other force? No. What we do have is we have A, but A is not normal A. A is A rad because you're going at constant velocity. So instead, A here is equal to A rad, which is equal to V squared over R, where R is the radius from the axis of rotation. When we write Newton's equations here, we write M A rad. Since we chose down to be positive, this is mg minus n, and let's solve this for n. N is equal to mg minus m A rad, which another way of writing that is mg minus A rad, but A rad is V squared over R. So the faster it goes, the smaller your normal force. I hope that makes sense to you. On the bottom, we still have N and we have weight is mg, but now since A has to point to the center, A has to go up. This is still A rad, so we get M A rad is equal to N minus mg, or N is equal to M A rad plus mg, which is equal to M V squared over R plus G. Now, what does this have to do with anything at all? If you've ever been in your car and you get dips on the road or been on a roller coaster, when you go up at the top of the hill, right, as you go flying over the top of the hill, you feel weightless. This is why you feel weightless. It's because if you go fast enough, you will actually get where V squared over R is equal to G, and you become weightless. You literally become weightless at that point. Well, what would that be? That's when B is equal to square root of RG. Let's say you're on a 40-meter Ferris wheel. So 40 times 9.81, or this answer is about 19.8 meters per second if R is 40. Let's say R is 40 meters. That would be a really big roller coaster, but, or I mean, a really big Ferris wheel, but maybe not that big of a hill for your car to go over. On the same token, though, if you go under, if you're driving in your car and you go down to the bottom of a dip, you kind of feel your stomach drop and you feel like you're like pushed in to your seat. Sorry, when you go up, you feel your stomach drop, right? When you go down in a dip, you kind of feel shoved down. The reason you feel shoved down is your normal force increases. It's a weird phenomena, but that's what it is. And that's about all there is to say to it. There, you just change A to ARAD, make sure it points to the center. There is one small problem, and that's that the normal force doesn't necessarily need to be on top of the C. There's this problem in your book where they have the motorcyclist daredevil guy. This guy, his normal force is actually down, and A is down, and his weight is down. And then at the bottom, his normal force is up, his weight is, his weight is still down, and A is up. If you do that problem, just know that that's what they're talking about. They talk about something about basically when he's just barely hanging on, that's when the normal force is 0. That one's not bad. What do you mean the inflection point here, Lucas, or for the dip problem?
Like, I'm just curious, like, where does your normal force like change from being up to down in that motorcycle
Oh,
problem?
this one?
Yeah.
I don't know, man. Because the way the normal force should be, it should always be pointing in the same direction as your acceleration. It's always pointing toward the center of this
I
guy.
mean, I guess it's always like perpendicular to the surface,
Right.
right?
Yeah.
Oh.
When you're directly at 90 and 100 or at 0 degrees and 180 degrees of the circle,
Yeah.
you're directly down, and your normal force is completely pointing inward. Weird, but yeah, I don't know. It's a weird problem, and whenever they try to do these problems of like things spinning inside with normal forces, it never works. They get away with it in this problem by saying, oh, when he's just barely in contact, so his normal force is 0. And it's like, I don't know if I buy that. I think the normal force is still there. If you don't believe me that it's still there, the only way that your wheels actually can go forward is if they're touching a surface, like if there's a normal force, and his wheels are definitely still rotating at that point. So I don't know. Investigate it, figure it out. It's annoying. It's an annoying problem. All right, so here's something that I want to touch back to from the beginning of class, or the beginning of this chapter. When I said that friction is like a simplified model, we can actually make a really hard model, and your book does, for fluids. Now, a fluid is anything, a gas or a liquid that you can move freely through. There's a long definition of what a fluid is that we'll talk about when we get to the fluid chapter 14. But basically, when you move through a medium, there's drag. So if you're falling out of an airplane and you're trying to catch terminal velocity, the reason why your velocity eventually hits a value, a final value, and doesn't increase anymore is drag actually counters your weight at that point. And we'll see that really fast. But this model actually that we're going to use for friction or drag in fluids actually doesn't rely on the normal force. You don't have a normal force when you're free falling. So how can you have drag? How can you have friction? Well, the answer is that as you fall, your body or a body runs into little molecules of air that slow you down. And so we need to come up with an equation for that. We're going to assume that it depends on your average velocity squared, that it depends on the density of the fluid. In a vacuum, you have no drag or air resistance. It also has to depend on the cross-sectional area. So imagine a big square sheet of paper falling, and imagine a wadded up little ball of paper falling. Which one feels more resistance? The wadded up ball. So it has something to do with what we call the cross-sectional area. And researchers love to throw a coefficient on there, which wraps up all the physics nicely in some numeric number. That coefficient is specific to object and fluid. So a human being swimming through water might have a certain drag coefficient. A shark moving through that same water may have a different drag coefficient. It's kind of like the mu for friction. So we put all that together and we get this drag equation. Coefficient, density of fluid, cross-sectional area, v squared times a half. If we assume that the object is freely falling, so it has a weight mg and its acceleration is down, and it has a force of drag opposite the acceleration, we get this nice equation right here. When the acceleration eventually becomes 0, we get mg minus force of drag. I'm going a little quick because we're almost out of time, and there's one important thing I want to cover after this. That says that when the force of drag and the weight are equal, you don't accelerate anymore. And that is a way of giving us the terminal velocity. So at some velocity, the force of drag will equal mg, and that take the square root. So let's talk about these coefficients before we find a terminal velocity. Density is how much per volume, mass per volume. For air, it's like 1 kilogram per meter cubed. For water, it's 1,000 kilograms per meter cubed. That means there's 1,000 kilograms or 1 kilogram of air in every cubic meter. There's 1,000 kilograms of water in every cubic meter of water. A is the face. Now, if you imagine a skydiver, spreading their legs out so that they can slow down, they have a much greater area than when they're head down, arms back, falling straight down. This area would just be the front part that faces the material that's trying to break through the material, what we call a face. And then finally, C, the coefficient is usually given or you solve for it. I gave you a drag question in the homework where you have to find, knowing the terminal velocities, you have to find the coefficients. It's not too bad, actually. So how would we use that? Imagine you drop a tennis ball or a rubber ball from off a building. You drop it. And it's a very high building, high enough that it's going to reach terminal velocity. We don't care how long. We could ask that, but we don't really care. If we did ask that, notice that the acceleration would not be constant. It would actually change, so we'd have to integrate the time, which is why we generally don't ask that. But this ball, I'm going to say, has a diameter of 1 centimeter. And it has a mass of 10 grams, 0.01 kilograms. The coefficient of drag, 0.8. The density of air is 1 kilogram per meter cubed. What is the terminal velocity? Going back to here, we know that if it's at terminal velocity, the weight and the force of drag are equal, and there's no acceleration acting on it. solving that for V and plugging in the various constants here, the mass is 0.01 kilograms, 9.81 meters per second for squared for acceleration of gravity. G or C was given, density of air, cross-sectional area. That's where things get a little tricky. Now, for a ball, it looks like a disk with an area of pi r squared or pi d squared over 4, because d is d to the half is r. So what I did here is I solved for a because they gave me the diameter. And so I got this number and I plugged that in and I got 55.9 meters per second. That seems about right for a ball. That's about 110 miles per hour if you dropped it off a very high building. Would it hurt? It'd be like a major league pitcher throwing it at you. Yeah, it probably hurt. But I mean, you're dropping it off a very high building. The important thing here to see, though, is that we've made a model that depends on the density of the fluid. So in water, which has a density 1,000 times bigger, if I multiply this, or I divide 55.9 divided by the square root of 1,000, I get about 1.7 meters per second that it would fall through water. The more dense the material you're moving through, the more drag. Something that weighs more is going to have a faster velocity. Well, something that has more mass is going to have a faster velocity. mg is actually the weight. So if it weighs more or if it has more mass, it's going to fall faster. Or at least it's going to reach a greater terminal velocity would be a better way to say it. And then the greater your surface area presented to the wind, the slower you'll go. That is why parachutists throw their arms out to slow themselves down. Yeah, it's a good model. It's closer than using some weird friction because it actually does have measurable effects, which is nice. The last thing we want to talk about are actually flat curves. And this is actually the funnest part of this whole chapter. So when you go through a curve, right? So imagine you're going through a curve at uniform circular, or yeah, UCM. That means that V is constant and A is ARAD. We can do a free body diagram here where we have a normal force and we have a weight. Remember that A has to go to the center in uniform circular motion. So that's ARAD, which is V squared over R. But then what do we have going on here? Now, overhead view of a car on a road. As it's trying to turn that way, so it's trying to rotate itself that way, it's actually pushing on the road. That pushing means that the force of friction is actually acting to the inside of the turn. It's the force of friction that is pushing you or pushing your wheels and allowing you to turn. That might be counterintuitive, but remember, when you're looking at a flat turn, there's N and W and ARAD. So you would have to have this M ARAD is equal to the force of friction, which is still mu N, right? So mv squared over r is equal to mu mg, this is mg, or canceling these, v squared is equal to mu gr. Now your book talks about something called lift. It's in this. Lift is just an additional force that pushes down on you. It's this, they call it negative lift, so that your normal force is actually now, this equation becomes MAY is N minus negative lift minus weight. So your normal force, and since that's 0, is equal to negative lift plus weight. That's like how much your race car is being slammed down to the ground. But basically, V squared is equal to mu g r, and V is equal to square root mu g r, right? If you exceed V, then you slide off the road. So let's say R is 100 meters and G is obviously 9.81 meters per second squared, and mu was 0.5. How fast could you travel that turn? Square root of 0.5 times 100 times 9.81 is 22. So V in this case would be 22.15 meters per second. That's only about 40, maybe 45 miles per hour. Why is this stuff important? I don't know how, if all of you drive, but those of you who drive, if you've ever looked at the on and off ramps or the ramps that take you from one freeway to the other, you'll notice that they usually have a speed limit sign on them. And that speed limit will tell you how fast you're supposed to take the turn. That is based on really bad tires so that they don't have good friction with the road. So basically, if you have bad tires, they go out and they figure out what the radius of the curve is. And then they figure out what your tires, if your tires were bad, how well your tires would stick. And they come up with a number. So you're driving a really good car and you're like, oh, I always take these turns at 50. Great. But when it gets wet and mu, which is the coefficient of friction, drops because the road is wet and now your tires aren't quite sticking, the velocity you need to, the maximum velocity you need to watch for decreases quite drastically in snow and ice, and it'll send you off the road, which is scary and something to think about. However, what if the road was curved and frictionless? And I'm running out of time, which is why I'm going to do this really fast. Let's say your car is on this turn. I do not want you to actually, in this case, don't do the trick of changing the whatchamacallit, the incline, changing the axes. Leave them alone. So what I have here is I have N and I have my weight and I have A points that way. So N I can break up into, if I look at this, this becomes, since this has to be 90 degrees and trying to remember, and this has to be 180. So this has to be 90 minus theta, or this is theta. So what you get is you get N is, what would that be? N sine theta, and this would be N cos theta, and this would be weight. So, and you have A rad. So you would get M A rad is equal to N cos theta, and N sine theta is equal to mg, which means that N is equal to mg divided by sine theta, and MA rad, which is equal to, if I m v squared over r, is equal to N cos, so mg sine theta cos theta. Getting rid of the m's, solving for square root, this becomes gr over tangent theta. Now, gr over tangent theta, if I solve that for So this is actually V squared is equal to GR tan theta. Remember, there's no friction here. So tan theta is equal to GR over V squared, or theta is equal to arctan of V squared. But let's solve for V first. If R were 100 and theta was 20 degrees, not quite what they do in NASCAR, but so 9.81 times 100 divided by tangent of 20 and taking the square root of that answer is 51.9. 51.9 meters per second. You could take a 20-degree bank turn with no friction if it had a radius of 100 at almost 110 miles an hour. If you ever watch NASCAR at Daytona and Talladega, they race on really high banked curbs. Basically, if you have banking, you don't need friction. So when you're driving on the highway and you see those banked turns to get you from one highway to the other, those are for snow and ice. Places with a lot of ice, they'll bank the turn because it keeps you from sliding off the road. It's really interesting. And you can solve for it using Newton's equations and friction or no friction for banked. This is kind of neat. For 100 meters, this is the speed you can have depending on how banked the road is. If you wanted to do, and remember, if you double this, you basically get miles per hour. So at 40 degrees, you could get like 56. I think I must have done something weird here. Something's off on mine, but essentially, a flat road without friction, you're going to slide off unless you go really slow, and you guys know that. So that's all good. You have homework that's assigned. It's due the Thursday of the test now. I'll move that back at some point. But you have that to do on Thursday. We're going to go over, we're going to review the homeworks and the sample tests. So as far as this stuff today, chapter 6 stuff, really it's just adding friction. And we'll talk about that in the example problems that are in the practice exams. I wanted to show you things that could go wrong today since I had the time. And then we can deal with how to make it right. So anyway, we're done. I went the full time today, which was a lot of talking, but hopefully the quiz today got helped you figure stuff out. So make sure you get it done and get it in by tonight, please. And otherwise, have a good day. And I'll see you on Thursday for review.
Thank you.
Thank you, Professor.
May I have a question about the homeworks?
Yeah.
Okay. So on homework, homework 4, question 4D, actually.
I'm opening it right now. Question 4D, you said?
Yes.
Okay, so you did see that it wants the positive number, right?
Yes.
Okay, so let me see. So what were you doing on that? How were you finding the vertical component of the velocity?
No, no. Let me actually open the. Oh, it doesn't open for me. It doesn't let me.
On this one, the one main thing to remember, Hamid,
Yeah.
this is a plane and that angle is from the vertical, meaning they gave you the angle from the y-axis So the initial velocity in the y would be cosine of that angle. Does that make sense?
Actually, I cannot open the homework. I don't know why. This assignment has
It's
blocked.
probably closed.
Was locked. Oh,
Yeah, it was closed on the 19th.
I cannot open it. Okay.
Hang on a second.
I had a
Let me
question
do one thing. Let me do one thing. See if you can open it. See if you can open it now.
Oh, sorry. Thank you.
Yeah, it's
Yeah. Yes. Thank
Okay.
you. Thank you.
so it's late now, but it's okay.
Yeah. No, actually, I'm done. I'm done with all the questions. But
So on this one, you needed to find y initial. So that would be cosine of that angle. So I don't know what your numbers are. I'm going to look really fast. What's your last name, Hamid?
my last name is Saebi Munfarid.
Okay, I'm getting there. Yeah, okay. So for question 4, it said that the angle was 43.7 and it gave you the altitude. So how high? That's y initial. You need to either assume y initial was 714 and y final was 0, which is what I would do. And you know the time. So you have the angle and you have the time, but you need to find the initial velocity and then use that to find the final velocity. The final velocity is equal to the initial velocity minus gt, but the initial velocity, how I would find that would be, hang on, can you see my screen still? Sorry. So on this one, what I would do is, since you were given the angle, you were given the time, and you were given y final minus y initial, that's really, you were given y initial. But what I would do is use y final minus y initial is v naught t minus gt squared over 2. Solve this for v naught t. So v naught of t is y final minus y initial plus gt squared over 2 and divide through by t. And then, and you know this is 0, this is whatever they gave you. G is 9.81, T is 5.6 or whatever they gave you. And then use V final is equal to V initial minus GT to get V final. Does that make sense, Hamid?
Yeah, but can we use this equation Vy equals to V naught sinus theta minus GT?
Yeah, so that's, you're saying V final is V naught sine theta minus GT, right? But you don't know this. You're going to have to find the initial velocity. And I don't believe it told you. It doesn't tell you what it is. So you're going to need some way of finding V initial. And I would suggest just doing this. You could also, I mean, yeah, I think that's the fastest way that you would find it.
Okay.
Because none of the, we only have these 4, right? We have y final minus y initial is v naught of y t minus gt squared over 2. And we have v final is v naught minus gt, and v final squared minus v naught squared minus 2g, y final minus y initial. And the last one is y final minus y initial is v final plus v initial over 2 times t. Those, remember, this is actually v naught of y. So These are actually V naught sine theta. But the only one that would give you V naught, I guess you can't find this one because you don't know V final. And you can't use this one because you don't know V final. And so I think the only way you're going to find it is that top equation, Hamid.
Okay.
That makes sense.
Yes. And homework 5, question 1C.